I think you'll be pleased you stayed to the end. Jun Ye is our last speaker. So Jun was born in Shanghai in China. He graduated with a bachelor's degree from the Shanhui Schawlow-Townes University. And you can correct my pronunciation. I'm sure it's terrible. I'm sure it's awful. He completed his master's at the University of New Mexico, working with Marlin Scully. And then he went to the University of Colorado in Boulder, where he worked with Jan Hall. And of course, that's where he is now. So he see that he got stuck in Boulder. It's a lovely place. His PDF was in Caltech with Jeff Kimball. You just heard Jeff Kimball speak. So you're now hearing his, one of his proteges. Jun returned to Boulder as a JILA fellow and a NIST physicist in 1999. So as I did with the others, I'll tell you a little bit about him. He's a fellow of the American Physical Society, the Optical Society of America, the Australian Academy of Science. He's a member of the National Academy of Sciences of the US and a foreign member of the Chinese Academy of Sciences. He's won a number of medals. He won the Lomb medal and the Wilhem Meggers medal of the OSA. He's won the Rabi prize of the APS. And in 2015, President Obama selected him to be for the President's Rank Award for Sustained Extraordinary Accomplishments. So it's a great pleasure to welcome Jun back to Ottawa and to hear him speak on, well, I didn't see again, but Jun, welcome.
Thank you very much, and it's a great pleasure to be here. I remember Professor Bob Ballard. Of course, we all know about the book. Whenever we have a book in the lab, whenever people try to calculate nonlinear optics, we always refer to this book. Paul, I got to know you very early on. I think in 2000, when I started working on frequency combs, I think one of the earliest colloquia I gave was actually in Ottawa here. You invited me very early on, was a very young faculty member at the time. But of course, the work that you have done here at Ottawa sets the stage of some of the revolutions that we have seen over the last couple of decades in laser science and attosecond physics. So it's a great honor to come here to celebrate Bob's birthday, but to participate in the symposium. And I want to come here, of course, also to honor the two leading intellects of our generation, our previous generation, maybe I should say, and Schawlow and Townes. One particular thing I think they enabled is this incredible pursuit of optical coherence because of their invention of laser. And I always feel Townes and Schawlow was a particular epoch in mankind's pursuit of light. Now, before them, we know of light. Of course, there's a Young's doublet measurements. There's all these philosophical debate. Is the light particle, wave? But light, we always categorize as a wave. After them, after lasers invented, I always feel the light is now digitized because it can be represented by frequency. And this is really the first time that, as you can see, some of the recent revolutions that in precision measurements and so on are enabled by this particular thought of you can synthesize electromagnetic spectrum of the entire visible radiation spectrum using digital techniques. And this is not possible without coherent laser that was invented by Schawlow and Townes. So I figured today, in 40 minutes or so, I would tell you a story about continuing to pursue that extreme coherence, both in terms of matter and quantum coherence, as well as in the light itself, optical coherence. And it's a very exciting time, as Jeff was saying. There's a huge quantum technology, quantum information science coming along, quantum sensing, many-body quantum physics, quantum information processing. At the same time, we are also at a very exciting time where you can pursue tabletop experiments that can reveal some of the deepest and yet undiscovered secrets of nature. Tabletop search of fundamental symmetries of our universe. So let's get on to that. As I mentioned, there are some things that we don't know, and some things we do know. For example, we know that the galaxy is spinning around the center black hole with a speed that's too fast. if you just accounted for the conventional gravitational physics. The stars which are far away from the center are still moving with a few hundreds of kilometers per second. And there's a dark matter halo. We don't really know what that is. On the other hand, it's also a very exciting time. For the first time, you can actually hear gravitational waves coming in, and milliseconds later and seconds later, you will see nuclear synthesis. And so things are really coming together. Quantum mechanics, high energy physics, gravitational physics, all coming together. What if we want to get into a day where you can build an atomic clock that you can hear about all these gravitational waves, and you can use that to search for the existence of dark matter? What kind of atomic clock we need to build? It would have to be built with accuracy or measurement precision at the level of 10 to minus 21. Because when you have a clocks reach this kind of level of sensitivity, when the gravitational wave comes, it's going to come in the form of the strain of the space or in the strain of time. It's a space-time is connected. And you will be able to just use 2 clocks to measure their relative time difference, and that will tell you the gravitational wave. And in fact, if you can get your day, get a clock to be so good, get to 10 to minus 23, 10 to minus 25, the gravitational wave will be all there. You'll be hearing this incredible music of the universe that's never quieting. And if you have this kind of a clock in space, you're building interferometer, you will actually be able to see as Earth, as our galaxy going through different forms of dark matter, whether it's being in the wave or in the form of domains. You will be able to use the clock interferometer, long baseline interferometer, to read out, to probe this existing, that we know dark matter act on gravitational sector, but we don't know yet how it connects with quantum mechanics. And clock, as I'm going to tell you, maybe provides a path where quantum mechanics and gravitational physics will be connected in the future, as long as we can continue to push on this level. 10 to minus 21 sounds fairly fancy for a dream for now. But consider how fast the whole field has been moving. I wouldn't rule this out in the next few decades that we might be able to get to that point. So where do you have this kind of confidence? Well, let's think about the time scales for a second. The life of the universe is about 10 to the 18 seconds. And then we deal with atoms and electrons moving around nucleus. And if we think of that's a quantum pendulum, the time scale associated with that is 10 to minus 15 seconds. So microscopic time scale to a very macroscopic time scale. If you take a square root geometrical mean, it's 30 seconds. And it happens to be, we have atom, which is a strontium. If you prepare coherent superposition between ground and a metastable excited state, it has quantum coherence of 160 seconds. If you can master the control of this extreme high quality clock, you can see that this clock provides means to connect from microscopic time scale, the electron orbitals around nucleus, to the very macroscopic time scale. Because if a clock like this would mean if you keep time at 10 to the minus 17 level, you would not lose a single second over the entire age of the universe. So before I speak about how we actually do that, there's a quantum uncertainty principle we all know. There's also a very trivial quantum certainty. But it's actually a very important part, which is that we all know electron orbits are quantized, and we all know the frequency between these quantized orbits are fixed. If you have done your frequency right, done your measurements right, they should all agree. And there's nothing uncertain about whether the population is the ground state or the excited state, as long as the population is actually in those eigen state of the Hamiltonian. What becomes uncertain is if you put your population in a coherent superposition between ground and excited state. And this clearly, it's not an eigen vector of the single atom Hamiltonian. So there's a phase, which is I dropped, a phase which is evolving with respect, because E has an energy difference from G, there's a phase which is evolving. And you can pictorially represent this as this block sphere. And when you try to make a measurement of how long this phase has been evolved, turns out there's a fundamental noise associated with this red blob that I'm showing. And this is associated with the fact that when you try to make a measurement, you don't know whether the atom is actually in the ground state or excited state. This is so-called a quantum projection noise. And so when you make measurements, what we do is if you have atom, Since photon is cheap, we can have many, many photons. We use classical phase of the laser to probe the quantum coherence of the atom. By using many photons to probe the atom, we can remove the noise associated with the photon, and the noise now is going to be limited only by these atoms. And if I can have many of them, then when you have many repetitive measurements of these individual quantum pendulum, the total noise of the system will go down as 1 over square root of how many pendulums you have, as long as they are independent. And in fact, one of the key frontiers in quantum metrology now is to make these quantum noise to be correlated such that the scaling can be even more favorable than 1 over square root of n. This is the so-called standard quantum limit. So this speaks about the importance of having really good laser. And laser is the central ruler of time and space. We are all familiar with laser in the form of what Townes and Schawlow told us. You have a cavity, you have a pair of mirrors, the optical wave going back and forth. I took the gain medium out. This is just in the form of the very simple Fabry-Pro cavity. And just for ease of discussion, let's put this cavity distance to be about 1 meter. The very best lasers we can make now can maintain coherence below 1 part in 10 to the 16. That would mean that the fractional fluctuation of the length would be at 1 part in 10 to the 16, or for this particular cavity, the actual fluctuation of the distance between the 2 mirrors would be at the level of about 1/100th of the nuclear diameter. If you can do that, then you will be able to generate a laser that's fantastically coherent. But what's the limitation? It turns out cavities like this is made out of a mechanical structure. You have either a mirror substrate or the coating, high reflectivity coating that's on top of the mirror substrate, or the spacer that's supporting the mirrors, making the cavity. All of these mechanical devices can be characterized as the so-called complex Young's modulus, that's how elastic the system is and how mechanically lossy this mechanical system is. And it turns out this particular quality factor, mechanical loss quality factor, provides, through the dissipation fluctuation theorem, provides the fundamental limit of the noise of a cavity like this, as long as the system is sitting at a finite temperature. Even if the temperature is absolutely stable, the fact that KT energy is being fed into particular each mechanical modes, and those mechanical modes are statistically independent. They are all being driven by this KT worth of thermal energy. When you add them up, look at the low frequency noise, this is a stochastic noise due to the fact that each mechanical mode has this KT worth of energy. And this is the fundamental limit and provides this very nice guideline of how we can think about the fluctuation length stability and therefore the frequency stability of a laser by finding a material with a very big Young's modulus, very good mechanical quality factor, and a potentially low temperature if you can. And this is the problem, in fact, cut across any optical science. The best interferometer we all know are thermal noise limited, and that ranges from very small nanomechanical oscillator that people are now driving these into the quantum mechanical regime, or a medium-scale optical cavity that I was telling you about for making stable lasers, or gigantic interferometers such as LIGO that people use to discover gravitational waves. They are all limited by the thermal noise. And therefore, many people across different disciplines of laser science and optical science have been working on this problem. And it's kind of interesting that some of the key insights we got of how to make a stable laser came from this community. I was talking with people like Marcus Espelmeyer and so on, and they said, well, we can make a very high mechanical quality factor thin films, and then if you can also make it optically reflective at a very high quality factors, then you can use those as mirrors, and we'll use that as a material to make an optical cavity. And indeed, that's born now a cavity that's made out of a silicon crystal, because it's a crystal, has a very, very low loss factor, mechanical loss factor. And you can have those mirrors also made out of a crystal of silicon, and then optically contact back up. So inside, of course, there's an actual hole there. The optical wave is going not inside the material, but it's still going through the vacuum back and forth. And the coating itself, we're about to put on the crystalline material coating as well. For the moment, it's not still amorphous coating. But with a material like this, with a cavity like this, we made a pair of those cavities. one for JILA, one for PTB, is actually the National Standards Lab in Germany, in Braunschweig. And when you beat those two cavities together on a photodetector, these are two completely independent systems, and you will receive a beat note on the order of 10 millihertz or so, indicating these lasers individually are phase coherent. Their optical coherence time is approaching a minute. And to just give you a scale, translating that optical coherence time to coherence length, just remember the distance between sun and the earth takes light about 8 minutes to go. So we can actually have a laser. If we don't have atmosphere, we can actually shoot the laser to the moon, and you can have a finesse of 100 cavity, and it actually can build of course, we're talking about large optics because of diffraction, but at least the coherence is actually there. You can bounce back and forth 100 times, and you still know which peak and trough of that light waveform you're sitting on. And I just want to recognize the graduate students and also wonderful collaboration with the PTB colleagues back there. So with this revolution, now comes another revolution, which is the optical frequency comb, where we can now make a very, very stable lasers at one particular color, as example I showed you for silicon cavity. And about the turn of the century, Jan Hall and Ted Hensch came up with this idea of so-called optical frequency comb, where you have a very digital spacing of frequency markers marching across the entire visible spectrum. Nowadays, we can actually make frequency combs into infrared and ultraviolet. So one single phase-stable laser can connect onto the entire spectrum of the visible light. So making a clock now turns into also control of the entire light wave spectrum, thanks to Schawlow-Townes for inventing those lasers for us 60 years ago. And so this is a stable laser delivers phase coherence of anywhere between infrared to extreme ultraviolet. So we have these fantastic tools of light, not quite yet at the level of where I said a 160-second coherence time. We have about 60-second coherence time. So we still need an effect of 3 or 5 to go. But by then, we will actually have a light that will be synchronized with the quantum pendulum, which has a 160-second coherence time. And that would be a fantastic way to build this clock. So now let's talk about how do we read out these quantum pendulum using such stable lasers. We all know that the trivial problem, the first order Doppler effect, if you have a light wave going across and shining onto the atom, if the atom is moving towards you, your frequency appears to be a little too blue. If the atom is moving away from you, your frequency appears to be too red. And if the atom is in a thermal ensemble, then your frequency looks really fuzzed out. That's first order problem. In fact, Schawlow back in the 80s and the 70s, so-called nonlinear laser spectroscopy, solved many of these Doppler problems. They invented a term called subdoppler spectroscopy. But the other problem, which is a second order Doppler problem, is just as important in the modern days of clock making. For example, if the atoms are moving at different velocities, we know that a moving clock moves a little bit slower if the observer is stationary. And also, Einstein said that there's a general relativity effect in a jar filled with thermal atoms. If the atoms at the bottom of the jar and the top of the jar, in fact, will experience different gravitational redshift, and they will have a different time. So you can be good about building a cell with those atoms, but they are all moving around with a relatively different velocity and sitting at a different gravitational potential, and they are all going to tell you a different time. So this comes across as a way to try to cool the atoms down using the technique, this very basic principle of Doppler shift and the photon recoil. We know atoms have a spectrum. You can absorb a particular light frequency at a particular color. So we also know about Doppler effect. So if you can find a way, for example, to tune the laser frequency just about the red side of the absorption of the atom, and when the atom is moving towards you, it will be Doppler shifted into resonance and absorb that photon and get stopped. I'm, of course, talking in a very simplistic manner, as if one photon will stop the atom. But that's the basic idea. You can scatter, if the system allows you to scatter many, many photons, you can actually stop the atoms. Just using those very, very basic principles. And in fact, this is what those three gentlemen did. They were able to put atoms in the thermal cell, and you shine laser beams from all 6 directions, 3 spatially orthogonal directions, but opposing each other. And atoms, when they were trying to move away from the laser beam, always gets pushed back by the beam, which is opposing their motion. And you can actually cool these atoms down millisecond time scale, as Jeff was wanting to do, and those temperatures will be dropped from thermal to something which on the order of microkelvin. And so it's an extremely efficient process. After that, we also celebrate this year's Nobel Prize. Ashkin, for example, in the 70s was already experimenting ideas of using optical tweezer to trap particles. And Steve Chu, later on after laser cooling was invented, started to trap atoms in the optical trap. And here's the idea where you have a ground and an excited state of atom as they move into spatially inhomogeneous laser focus. At the center of the laser focus, the polarizability of the atom gets pulled into it because of they get a bigger AC stock shift. The inhomogeneous AC stock shift provides an optical trapping potential. And that's the basic principle of optical tweezer. We came up with a little twist on this, and this was work actually when I was a postdoc with Jeff, and we were actually working on these ideas independently, Kotori in Japan, which is for precision metrology. Actually, you want to create a trap where the ground state and the excited state frequency shifted exactly the same way, AC stock shifted, such that as you make a measurement, you're trying to measure the energy difference between these 2 atomic states, and you want to do that inside the trap. That's the whole point of keeping the atom at the tip. And then when you make those measurements, you don't want that tip, which is holding those atoms, influencing the measurement of the clock. So this simple trick allowed us to actually hold atom in this so-called magic light, where you can, on one hand, hold atoms, on the other hand, characterizing the inference and minimizing it. And the most simplest possible realization is just send a single laser beam, retro-reflected by mirror, and you form a standing wave. Everybody does that all the time. And this standing wave will allow you to form a stack of pancakes, and you have a dozen of atoms, or a couple dozens of atoms can be trapped on each individual 2-dimensional traps. And then, of course, the distance between pancake is exactly lambda of 2. And you can actually visualize this Doppler effect very interestingly. Just as you form, this is the Doppler effect, for example, as you start. And as you form this pancake initially with very little light intensity, you form this pancake looks like this. Now we start to speak in condensed matter language, as Adina was telling us about all the band structure and so on. Towards the end of my talk, you will see that we are converging towards condensed matter, that our atomic clock will be like a man-made condensed matter system. And here's the starting point. As you modulate the spatial structure, the Doppler frequency will be modulated. And as this well gets deeper, you start to see the Doppler frequency. Doppler is still there. It just gets digitized. It just gets quantized. This is actually a Doppler effect, but we can call this as a sideband, which is actually the atoms rattling around inside each individual well. And you can start to be, instead of having a band where they can be conducted, now you start to localize with individual one-year functions. And that's where the individual oscillation frequency in each harmonic well is being reflected here as a Doppler shift. But you can see this Doppler shift is far away from the carrier. This carrier is Doppler free. So if you want to make an atomic spectroscopy or clocks, you like to have this particular transition that is basically the free atom transition frequency, has no Doppler shift, has no AC stock shift, and has no photon recoil, because we can confine these atoms in the trap so deeply that atomic recoil frequency can be suppressed. And so this is a line that we use to build a clock. And this is, in fact, following exactly the lead of Dave Wineland and Serge Haroche. They were celebrated in 2012 with Nobel Prize because they really pioneered the way to control individual quantum systems. In Dave's case, Dave Wineland's case in particular, with the trapped ions, he was able to very cleanly separate the internal degrees of freedom, G and E, from the external degrees of freedom, which is ion trap in his case. In our neutral atom case, now with the symmetric wavelengths idea, we can finally also achieve the same goal. But of course, neutral atom holds an advantage where you can scale things up. Indeed, we are not satisfied with just one atom in there. We want to put dozens of atoms per pancake, and we want to have hundreds of pancakes. And this will allow you to have thousands or tens of thousands of atoms to allow you to improve the precision by square root of the number of atoms that we have. And indeed, this is the basic principle behind that some of the very best clocks that we are now making, reaching accuracy and a measurement precision now actually going to 10 to minus 19s, but accuracy at a few parts 10 to the 18th. And just to show you, these clocks are no longer just confined in a particular lab. Here, and several talks today already talked about air links. And we have done our own air links where the JILA campus and the NIST campus can now have lasers going back and forth. And these lasers can actually be used to across about 2 kilometers of distance. And you can actually transmit these clocks at the level of 10 to minus 18. And we also have optical fibers linking the two campuses. And we can compare both through air link and the fiber link using clocks in my lab and the clocks in NIST main campus. There's a trapped aluminum ion clock and ytterbium optical lattice clock. And this just shows one particular days of a data set where the ytterbium strontium, both are the lattice atom, can average it down to 10 to minus 18 or so. And in fact, all three clocks now have been characterized through this so-called three-corner hat measurements at the level of 3 or 4 times 10 to minus 18. So this is a basic historical chart of the advances of the clock uncertainty over the years. After World War II, this microwave clock coming down steadily, and optical clock really took force after the 1990s and the turn of the century after the comb was invented. It really came down very fast, right now at the level of few parts 10 to minus 18. And just to summarize some of the enabling ideas and why this is still going really fast, by being able to use very high quality factor optical transitions and to do quantum state synthesis based on single atoms and controlling multiple atoms, using new laser stabilization techniques to achieve very long optical coherence time, and use many, many atoms, and together with long coherence time, with perturbations understood at a small systematic level, and along with the optical frequency comb, all these together that really fueled the development over the last few years. And I would say the next goal, and which is in the remaining end, how much time do I have?
I didn't look carefully, but
Okay.
another 15 minutes.
Okay. Is I want to tell you about how do we go to 10 to minus 20, 10 to minus 21, as I showed, the kind of idealistic outlook of going to 10 to minus 21 to 10 to minus 22. So one of the issues that we faced at the time is that when you put many, many atoms into this very tiny space, and there's inevitable these atoms going to rub shoulders. If they come close and they have a collision, the frequency could be wrong. And that's actually one of the reasons that, remember I said that we have dozens of atoms per pancakes in these traditional optical lattice geometry. And we pick the atoms to be fermion. So the fermions obey Pauli exclusion principle, and that in principle that tells you the two atoms would not want to come close to each other. And that's true. So fermions have much lower collision loss rate or collision frequency shift compared to bosons. But the problem is that the next order of the partial wave would be the so-called P wave. Even though the two particles cannot have a head-on collisions, they can circle around each other. And this is the so-called P wave, where you have a 1h per unit of angular momentum with the two atoms circling around each other. And over given enough time, they will develop a frequency shift. And in fact, we can see that very well. These are the dozens of atoms confined in this two-dimensional space. And here's actually in the momentum space, I drew these atomic energy level structure due to the motional states. And each atom is going back and forth in x direction and the y direction with their eigenfrequencies in these harmonic traps. But they run into each other, they collide with each other through this P wave. And this P wave can actually give collective frequency shift in the sense that when I'm driving with my laser to try to tip the spin from the south pole to the north pole, remember this is a Bloch sphere, but when these spins start to interact, especially even if the interaction energy is low, in my case it would be on the order of 1 hertz or so times Planck constant, given the time that we have now very, very long coherence time, 1 hertz times 10 seconds is much greater than 1. And this what actually means is that those quantum fluctuations of these individual particles, this so-called projection noise, now become correlated. And you can actually see non-classical spin noise that's twisted. The original sphere of the spin noise distribution is now become elliptical. And so you can actually turn this into an opportunity to study spin many-body physics. It's actually quite an interesting condensed matter problem. But for clock, this presents a problem. For example, we can measure the frequency shift as a function of the tipping angle on this Bloch sphere associated with these P-wave interactions. And you can always say, well, why don't you park your frequency, park your tipping angle right at this point where you have a zero crossing, so the frequency shift will be 0. But turns out, because they're so strongly interacting, it's kind of funny for me to say strong interaction because these are very weakly interacting systems. But because your coherence time is so long, after you waited for a long time, it is strongly interacting systems, just very different from attosecond. But the actually many-body aspect is very similar in that regard. And that's the beauty of physics. You can scale things up and down according to the interaction energy. This strong interaction actually prevents them from flipping up. There's actually interaction blockade effect. So this actually starts to affect the contrast, coherence contrast of these clock system. And this really is behind the motivation of developing the so-called three-dimensional Fermi insulator clock. You can see now I'm starting to borrow the language from condensed matter. What do I mean insulator, right? It's not like I actually have a chunk of a solid state. It's still atomic physics, still atoms. But if we can put atoms one by one in a three-dimensional optical lattice, instead of just having one beam in one direction, you have three beams intersecting and interfering. You can create a structure like this. If you have one atom per site, then in principle, they never run across each other. And by Pauli exclusion principle, only one atom can sit in one site. And that way, if I can scale things up with 100 by 100 by 100 cells, you have a coherence time of 160 seconds. You can actually start to imagine you can build a clock, even with 1 second waiting time, you will have a precision of 3 times 10 minus 20. So 100 seconds later, you will be at 3 times 10 minus 21. 1,000 seconds later, you can start to hear gravitational waves. And so, we are not there, but it looks like it's actually an approach that it's worth pursuing. And in fact, these graduate students and the postdocs, they jumped into this project 2 years ago, and we actually made quite a bit of advances over the last 2 years. That's what I'm going to tell you. So how do we make a Fermi gas Mott insulator? We start with quantum gas, degenerate quantum gas, and we load them in 3D optical lattice. It looks like this. And if you don't believe me, I can show you some measurements. For example, it's a gas, right? If you release gas, what do you see? The gas is going to expand spherically. But in this case, when you release the gas, it expands like a square. And that's because you load them in the lowest possible Brownian zone, and they can only expand plus minus h bar k. So I want to point out again, these pioneers give us the quantum gases, Bose gases and Fermi gases. And particular Fermi gas was a gift from Deborah Jin. And so with these systems, if you load into the optical lattice, we can also do spectroscopy now. Remember I showed you the sideband, and I said that's quantization of Doppler effect. Now you have 3 different directions of X, Y, Z. They are all showing the sidebands, which when the atoms are in the lowest possible band, when you drive them, you can only put one phonon into the system. You cannot take a phonon out of the system. Therefore, there's no red sideband, only blue sideband. So all of this is characterizing that you have indeed atoms loaded into the absolute lowest possible quantum state in all 3 directions. And if you insist, it turns out this atom has a nuclear spin 9.5. If you insist all 10 nuclear spin states are loaded, because the different nuclear spin states are considered those particles no longer identical, so you don't have a Pauli exclusion principle, you can actually have multiple nuclear spin states loaded in here. And if that's the case, when you try to drive the clock transition, what you see is, again, a single carrier frequency here. Now these are interaction due to the fact that when you have a nuclear spin and electronic degrees of freedom, the total wave function always has to be anti-symmetrized because those are fermions, but the anti-symmetrization can be done through the nuclear degrees of freedom or the electronic degrees of freedom. That's why there's EG plus, EG minus, and these are the peaks you can see. They're kilohertz away from this transition, which is supposed to be a few millihertz wide. So These effects, the interaction used to be considered a big problem in clocks, and usually it's come in an analog way. But you can see by confining them in the optical lattice, interaction effects, just like a Doppler effect, have been quantized and removed. These frequencies won't cause frequency shifts on these carrier transitions. So that's another layer of problem that's removed. And not only we can, in fact, you can do a lot of beautiful physics with this. Not only you can see 2 peaks, 2 plus, 2 minus, you can actually see 3 plus, 3 minus, 4 plus, 4 minus, and so on. In fact, you can see the whole distribution of how this quantum matter arranges itself with a lot of nuclear spins, and how they want to, 5 of them sitting in the core, 4 of them sitting outside, 3 of them sitting outside, 2 of them, 1. You can see those shells. And that can be just beautifully revealed by clock spectroscopy. So if we focus onto the single particle per cell, you have this coherence time now, the longest coherence time people have seen between atom and light. And using this, you can achieve, in this particular case, 10-second coherence time. And you can use this to build clock. And here shows the single clock stability of 5 times 10 to the minus 17 per root tau. Fairly far away from what the number that I promised you, but looks very good. It's the very first try is already exceeding any of the previous effort in the 1D lattice clocks. We can also take images. These are the atoms that's being confined in the 3-dimensional optical lattice. You can put a microscope on top of it, as learning from biologists and condensed matter physicists. And you can see the atom distribution in there. And it's like looking at every clock, finally, in your view. And what's nice is, for example, if you want to measure gradient, you apply a small magnetic field gradient, and you can take a camera shot, and you can actually see the fringes of atom being excited, not excited because there's a Z-man shift, excited again, not excited. It's just one shot burns in this atom-like coherence is not in the spatial image. And you can use this to measure the gradient forces of different things. For example, we all know that atom has a gravitational redshifts, the internal degrees of freedom. Our 3D lattice is being done in the laboratory, sitting in the frame of Earth. If the clock continue to make extreme advances in the future, that we will be able to look at the time difference layer by layer. And this will be the first time, I think, that we all know that redshift is nothing mysterious anymore. It's a very classical GR, predicts the redshift, has been confirmed everywhere. But I think it will be the first time you can look at a redshift on atomic coherence scale, where you can actually have a coherent atomic wave going block oscillation back and forth, and the proper time is different as it propagates in different sites of the lattice. And clearly you can make measurements across the surface in the horizontal plane, in the vertical plane, and they will give you a different physics. So to just conclude, let me tell you, I only showed you 10-second coherence time. Where is that 160 second? And I want to conclude to tell you this final 2 slides on that. We can load these atoms in the lattice and can live there for 100 seconds. So we thought, okay, it's promising. We're going to get to this natural lifetime of the atom coherence time. But then when we put them in coherent superposition and look at the Ramsey fringe contrast as a waiting time, it looks like the coherence decays away, and by 20 seconds, the contrast is fairly low, only 20%. And when we look at actual population, it's not because of actually there was coherence problem. It's actually not the so-called T2 problem. It actually turns out to be the T1. What is T1? The population is actually changing. The excited state population is decaying. The ground state population is gaining. And turns out the problem is due to the fact that we are very proud of this magic wavelength trap, 813, that gives you the same polarizability of triple P0 and singular S0. But the triple P0 is still lying closer to upper electronic states. This 813 is doing Raman scattering, putting the population from triple P0 away into triple P1, or triple P2 for that matter, but triple P2 gets pumped back by the Raman process. And then triple P1 has a decay channel, goes down to singular S0. And this process we now understand extremely well. We know exactly why we see only 20-second coherence time is because of this process. So what's the solution? The solution is we must reduce the lattice intensity. The lattice is too strong holding them. And this is really the final slide. It's a really interesting story I want to tell. It turns out there's a really interesting spin orbital coupling story here. So suppose you have just two wells with one fermion, and this one fermion can tunnel back and forth. And this is where the problem can come. When your lattice is too shallow, the atom is going to jump. This tunneling we learned from condensed matter physics. But the clock laser, remember, it works at a 698 nanometer. That's at a wavelength that's given to us by the universe. That was born when the Big Bang was made. So that wavelength is fixed. The magical wavelength, which gives us this very nice matching the trapping potentials between ground and excited state, also has a fixed wavelength. And if you just put them together, the wavelengths don't match. That spacing, lattice spacing A, does not equal to lambda of the clock laser. So if the fermion hop back and forth when the lattice is too weak, then you will see that at this position, it will have this, pick up this phase shift. But if you go to the right-hand side of the 2L, it pick up a different phase shift because the clock laser carries a phase e to the IKA. This K is the clock laser wavelength, A is the lattice spacing. So one trick to solve that problem, and that's why so far all the experiment we have done is always making the lattice really deep, so this tunneling T is 0. But if the tunneling T has to be there because we have to solve this problem of too much scattering, then the idea is to just pull the spacing apart a little bit. How much apart? To be roughly equal to the lambda, for example, of the clock laser. If that's true, e to the IKA equals to 1. And so even if the atom can still jump left, right, left, but their jumping is exact integer multiple of the wavelengths, therefore there's no phase shift. So it's like a Doppler problem, but it being exactly digitizing away. And you say, okay, we can, oh, that sounds like a good idea. We can do that. The lattice doesn't have to be formed by just retroreflecting. You can actually have two beams coming in with angle and tuning the angle just like an accordion way. You can actually tune the lattice spacing to be matched. But the problem is if you calculate how well this really has to be matched for the clock accuracy, this theta would have to be on the precision level of 10 microradian. And I know it's very difficult in the lab. It's impossible nearly. And so the real solution to this problem turns out to be you just have to remove all the entropy out. Instead of one fermion with two wells, which has an entropy of kb log 2, if you actually have two fermions with two wells, you solve that problem. That's because when the fermion trying to jump onto the next well, there's interaction energy. The two atoms coming together. Remember, I measured those interaction energy for you. So the process of tunneling is no longer T if the well is already occupied. Rather, it's given by second-order perturbation, the T square over U. If you make U really much bigger than T, this term goes to 0. And that means you can actually get to a regime where the lattice is just a few recoil deep, and the T square over U is still much smaller than 0. It's still close to 0. Therefore, these atoms are frozen. And this is so-called a band insulator in condensed matter language. If you have one atom in this well, you just cannot go to the next one if that next atom is just going to give you an elbow to push you out. And that's the scheme we think will eventually get us to 10 to the minus 21, 10 to the minus 22. It may not happen tomorrow. It will probably take 20, 30 years. But I think it's very promising. And with that, I want to thank all these many wonderful people who have contributed on Strontium for the past, I think we have been working on this for 18 years. Since I've known Paul, we have been working on Strontium. And these are the current set of people that you have seen their faces during my talk. And I also want to acknowledge collaborations, particular theory collaboration with Anna Maria Ray, and the NIST collaboration and the PTB collaboration on the stable lasers. Thank you very much.
At the very beginning of, great talk, first of all.
Thank you.
At the very beginning, you had a slide called the world's most stable laser, made of silicon, I think?
Yes.
What was the gain medium?
Oh, sorry. It was misleading. It's the most stable cavity, rather, I should say. The laser itself is a...
It's a cavity.
The laser itself...
It's a cavity to filter the laser frequency.
Yes, exactly.
Understood.
Yes. The laser itself is actually ordinary diode.
It's just a diode.
It's just a diode. And so the traditional line width of tens of kilohertz. But because we have this cavity is so stable, we can stabilize the laser frequency onto that cavity. So together, the diode laser plus the cavity forms the most stable laser.
Got it. Thank you.
The frequency doubling tricks we learned from your book. Because it's a 1.5 silicon cavity, only transparent for 1.5 micron. Strontium transition is at 698. We need to do a frequency doubling.
So when you started out, I was sure you were going to say something about nuclear transitions to get to 10 to the minus 22. Do you think you can get to 10 to the minus 22 without ever looking at nuclear transitions?
Yeah, it's an excellent point. The nuclear transition, people are looking for it, and it's getting more and more promising. Yes. But if you think about the path towards this 10 to minus 22, I think one guy, one nuclear transition, unless the Q is already 10 to minus 21, with one particular transition itself won't do it. Because you need a lot of measurements to be able to average it down. Just like a single trapped ion right now, you can have a fantastic accuracy, for example, but just takes months to average if you start with 10 to minus 15 level. The nuclear transition is promising. However, look at the quantum state engineering that's been happening for making this very fast clock requires you to, that nuclear transition is, yes, shielded away from black body and so on. But just the fact that you have this sitting on the podium is going to have a huge amount of Doppler effect. So how do you cool the system around it? How do you put a multiple of the system together? It's all going to be something that you have to work out, just like I'm talking about today. And so I think continue to chase for the highest possible Q quality factor is important, and nuclear transition may provide such avenue. But I think still require also simultaneous work on being able to have many of the quantum systems together and precisely control them together.
So thanks a lot. The remark you just made that a single ion cannot do this because you have to average so long. That reminds me that before you said you compare with the aluminum ion
yes.
clock, which is a single ion.
Right.
And I thought at the moment aren't you kind of like in a head-to-head race between the strontium lattice and the single ion? I mean,
the comparison in terms of the short-term stability, you can actually see the ion, for example, in each day, it never averages down to below 7 times 10 to the minus 18, just because of the fact that the ions. So you can see on that, oh, not here. You can just see on this curve, both the green and the red points with the participation of aluminum ion. And in fact, it's amazing. Whether you're comparing against yttrium or strontium, it really doesn't make a difference. It's just limited by the aluminum ion's short-term stability. So as long as the accuracy is good, you can keep averaging. And the yttrium strontium, for example, is at here, but this actually includes the entire loop and so on. And in principle, that what I'm talking about, that we will continue to push on the precision measurements, which is now starting at a mid 10 to minus 17 coming down. So that's the comparison.
But it's still amazing they're not so far behind.
Yeah,
so it's less than a factor. What is it? A factor of 4, 5, 6?
In terms of actual stability, yeah, something factor of this is 3, this is maybe factor of 8 or so.
And you have how many strontium?
In this case, 1,000. This is the 1D.
Okay.
This is the 1D system, and in fact is limited by how many atoms you can use. Remember, I was talking about the collisions per pancake. So 1,000 atoms take a square root is a factor of 30.
Mm-hmm. Okay.
And still actually also limited by the laser. Whenever you are collecting atoms, there's a Dick noise in the system.
So this is real quick. What are the units of sensitivity? You say 10 to the minus 20th.
What's the unit?
What are the units?
That's the fractional unit. Just like it's a fractional unit.
Well, I thought it was per root hertz.
Oh, so
That's
yes, per root hertz is
And
just
while
a
you're at it, what is an Allen deviation?
You're correct.
So I guess this is not a short question.
No. So you're asking an excellent question. So if you're talking about measurement of noise always associated with the bandwidth, right? Because basically is a statement of saying if your average time is longer, depending on the noise characteristics, can have different average behavior. So indeed, whenever you say it's a fractional number, you're getting to a precision of certain numbers. You should always say what is the average of time you have done. So because you said 10 to minus 21, that depends on how you get to 10 to minus 21. It maybe if the three-dimensional clock with 1 million atoms actually work, you could get 10 to minus 21 in just 10 seconds. Or with the current technology we have, we started 10 to minus 17. In order to get 10 to minus 21, you need 10 to the 8 seconds. So it will take a long time to go there. And before you get there will be systematic effects.
So when you were quoting numbers, they were just the fractional uncertainty. It's a fractional error in units of seconds, for example.
Yeah, it has both statistical part and the systematic part. Just for example, I give you, say, gravitational wave detection. When they say we heard the gravitational wave, they are measuring the strain, delta H over H. And that's also 10 to minus 21, 10 to minus 22. But there's a bandwidth. This was measured at this particular Fourier frequency with how much time you averaged. So there's always per loot hertz, that kind of normalization factor associated with that. And I'm quoting the same number here.
Okay. Thank you.
Yes.